start, let's talk about the big deadlines. So, for those who are not in last Thursday lectures, the professor has postponed the homework due date for the last week homework. So it's not due on Sunday; it's due on 24th of July. So if you haven't finished that, let us know. If you need us to help you with any kind of questions, come to our office hour or ask us before or after the lecture. Okay? Okay? I know that the questions is going to be more tricky lately because as the semester progresses, we get harder and harder questions, but yeah, and sometimes the questions asked on Alex are way harder than the one that you will encounter in exam, and we understand that. But the professor insists that she put it there so that you guys can think more about what's actually going on instead of just handle the questions we gave you directly. It would be beneficial to all of you in the future. And next Monday, you guys will be checking out, and the exam is on next Wednesday. And note that I will not be checking everybody out next Monday. I will ask one of my friends to help me in checking all of you out because I have to go to a conference and it's not near Purdue, so I'm not going to be there. So next Thursday, this Thursday will be the last time we meet in the summer. Okay? Okay? And yes, Professor Cindy will not be here during the final exam too. So now let's talk about the lab. Oh, wait a minute. Before I start talking about next lab, do you have any questions about the second exam? Do you have any questions about the second exam that you want to ask? If you find some of the questions you should have gotten right, but you didn't, feel free to bring it up so that we can kind of solve that problem for you. You need to remember that in the final exam, it's cumulative. So whatever you got asked, there's a chance that the professor will ask you again because you know that, during the second exam or during the first exam, a lot of you made this mistake, and I explained those questions in the lecture already. So we expect you to at least understand more than when you took the exam, the first and the second exams. Okay? Okay? So now let's talk about the next lab. The next lab is called iron deficiency test. So your only goal is to find out which patient, either patient A or patient B, has an abnormal serum iron level using visible spectroscopy. Essentially what you are going to do in the lab is like what you did for the copper in the Penny lab, but this time you're analyzing iron instead of copper. You're analyzing Fe instead of Cu. And note that in living organisms, our blood contains iron in the form of iron 2 plus and iron 3 plus. So in the lab, to simplify the analysis progress, we will use hydroxylamine NH2OH to reduce all the iron 3 plus into iron 2 plus. You will learn about reductions and oxidation in the future, but now you just need to know that the reason why you will be using this chemical in the lab is to reduce all the iron 3 plus in the sample into iron 2 plus, so that when you're measuring the when you're performing measurements in the experiment, you are only measuring Fe2 plus. You are only measuring Fe2 plus, and you will be using ferrozene to bind with Fe2 plus and form a purple complex ion, just like what you did with adding ammonia into copper last time. Remember, copper 2 plus is light pale blue, but once you add ammonia in it, it becomes deep blue. It's easier for you to perform visible spectroscopy if the color is deeper and more obvious. Okay, this time it's the same thing too. Fe2 plus, when the concentration is very low, it should be colorless. When the concentration is really high, there's a chance you can see a tint of green like Janice clothes, but that has to be very concentrated. So, and in our bloods, we don't have that high amount of Fe2 plus or 3 plus in our bloods. So we need to use some like enhancer to enhance the color. And in this case, the enhancer is ferrozene. It's a chelating agent. It will form purple complex ion with Fe2 plus. So, assuming in all of the in the experiment tomorrow, you will be convert all of the Fe2 plus into the complex ion. What's the molar ratio between Fe2 plus and the ion complex ion? Fe complex ion.
1 to 1.
Catherine?
1 to 1.
So 1 to 1. So tomorrow in the final lab report, we will be asking you to calculate the standard concentrations of Fe2 plus in all of the standard solutions. And later in the sample solutions, when we will ask you to do that, actually we're asking you to calculate the concentrations of the complex ion. Okay? But you don't have to care about that because the molar ratio is 1 to 1. Just do what you would do when you're calculating the concentrations of Fe2 plus in the solutions after dilution. Just treat the questions as if you're performing dilution calculations. Okay? We'll talk more about the mathematics later. So now, this is the molecule, it's huge. This is the chelating agent, the ferrozene that we were using. Note that you can see one nitrogen and one nitrogen here, right? Nitrogen, carbon, carbon, nitrogen, nitrogen, carbon, carbon, nitrogen. This is the part where the chelating agent binds with one Fe2 plus ion. And 3 of the chelating agent will bind with one Fe2 plus. So what you see is something very complicated, that's why I didn't draw it out, but you see something that looks like this. The silver sphere is the Fe2 plus, and the NCCN, you're seeing it's binding to the Fe2 plus. So it's like this. NCCN, oh, I ran out of blue sphere, that's why. NCCN, 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 so it binds like this. So for Fe2 plus, it's a 6 coordinate. It's a 6 coordinate products. Okay, but it looks like this. Very hard to draw, that's why we're not drawing it out. And you don't have to know how to draw it. This is how you know, this is how the complex look like visually, a simplified version. So, some general notes for the experiment. You will be performing the experiment in a group of 2. Not in a group of 4. In the lab manual, it's set in a group of 4, but last time we tried that, it's too simple for everyone to, the experiment is just too simple for you to do that in a group of 4. So you need to do that in a group of 2. Bring your laptop, your lab manual, and the calculator to the lab because we only have one bench computer on each row, and you need to, each of the groups, all groups has to come up with their own calibration plots. That's why you need your laptop. And each group only analyze one sample. Only analyze one sample. And so far we have 1, 2, 3, 4, 5 groups. That's why we only need sample A and sample B. So tomorrow we will not be using sample C. Okay? And you need to count, this time it's a little bit special, but because you don't have to calculate the concentrations in terms of molarity. You will be calculating the concentrations in terms of microgram per deciliter. Microgram per deciliter. For those who are in health science divisions, you notice that this is the unit you use more comments than molarity. Why? Because it's easier for you to just weight something and then use that in the concentration. And because when you're drawing human bloods or when you're collecting liquids from plants, the amount is not how many milliliter, right? And it's way bigger. That's why we're using deciliter. It's a bigger unit for volume, and gram is easier to measure because you just got it directly from a balance. And the reason why we're using microgram per deciliter is because in human bloods, you don't have kilogram of iron. You don't have grams of ions. You will die if you have that amount of ions in your blood. So we only have a trace amount of ions in our blood. That's why we use microgram per deciliter. Micro, you need to write it out somewhere in the useful information at the bottom of your recitation guide. Micro means 10 to the minus 6. And deci means 10 to the power of negative 1. So, 1 gram equals to 1 to the power of 6 microgram. The unit is small, that's why the number is big. this is the conversion unit you will be using in the pre-lab assignment if you haven't done so. 1 liter is equals to 10 deciliter. You can flip the unit if you need to during the calculation in the pre-lab assignments. Okay? So, that's it. And you will, because the solution, tomorrow you won't be dealing with more than 1 milliliter of solutions, because you're going to do all the mixing and all the sample preparations or solutions preparations inside the cuvette. You're not going to use any volumetric flask or test tube, because in real life, when you get bloods from a patient, you're not going to get 2 liters of bloods out of a living human, right? You're going to get around 10 or 20 milliliter. That's too much, a little bit too much. 10, yeah, about that, like 2 tubes of blood. So every drops of bloods are very precious. You will only analyze that amount of bloods. So you try to mimic what's going to happen in the real life. That's why tomorrow you will be using pipetter to dispense solutions instead of a big pipette or a burette. So, how many of you have seen a pipetter before? Good. Huh, great. So how many of you have used a pipetter before? Okay, so tomorrow I need to focus on like 2 or 3 groups of students and teach them to do that. Great. So, you know how to use it. We use that to dispense solution that's less than 1 milliliter. You can go down to, I think the minimum could be 2 microliter. Or if you really want to push it, 0.1 microliter, but the volume's not going to be as accurate. Yep. So, turn in your pink note individually by the end of the lab, and turn in the final report with 1 calibration plot as a group by the end of the lab too. A student from Kevin will be responsible for the cleaning of the lab, because it's easy, you know, I can do that. So, let's talk about the lab step by step. First of all, you need to start by calculating the concentrations of Fe2 plus in terms of microgram per deciliter in all standard solutions. And the fact is, you can do that tonight while you're completing the pre-lab reports. Okay, while you're completing the pre-lab reports. Hint is, those numbers are the multiples of 5. Those numbers are the multiples of 5. So when you're calculating, if the number is really pretty, it means that there's a chance that you got a correct answer. And the second is you have to prepare. The second step is you have to prepare a blank solution in cuvette number 1. Note that if you read the recitation guide carefully, you will be using 3 cuvettes, and you are not supposed to mix them up. The first cuvette is for blank solution. The second cuvette is for standard solutions. The third cuvette is for the sample, the unknown. Okay, so you need to prepare the blank solution in cuvette number 1 by mixing 1,000 microliter of water, 50 microliter of hydroxylamine, and 500 microliter of hydroxylamine, and 500 microliter of the chelating agent. And note that in this experiment, because the chelating agent is very sensitive to Fe2+, if you're using the Fe2+ you got from the tap, or the Fe2+ you've been storing in your drawer for weeks, there might be contamination. That's why we will be providing you pure deionized water prepared by Jeannie minutes before the experiment start. We're going to put that into the main hood. You will be only using that deionized water throughout the whole experiment, except cleaning. Okay, am I clear? So, after that, you can set up and calibrate the spectrophotometer. You have to scan standard number 3 in cuvette number 2 to find the lambda max at the absorbance at that wavelength where it has the maximum absorbance. Note that in this experiment we have already prepared all of the standards for you. So tomorrow when you step into the lab, you will see 4 different solutions with different degree of purple. And those are your standard solutions. You don't have to mix them with anything. Those are ready to use. Just grab them and put them into the cuvette and measure the absorbance. Okay? It's going to be relatively a quick lab. And after finishing finding the wavelength for maximum absorbance, for standard number 3, do the same thing for standard 1, 2, and 4, and then construct a calibration curve, just like what you have been doing. But this time the x-axis is in the unit of microgram per deciliter, because that's the concentrations of the standards we will be using this experiment. And then for sample analysis, you need to load 1000 microliter of serum sample into cuvette number 3, add 500 microliter of hydroxylamine and 500 microliter of chelating agent into the cuvette and mix it well. And in this step, actually, you have unintentionally diluted the concentrations of the sample you're analyzing, right? You have 1000 part of your sample and you add 500 part of hydroxylamine and 500 part of chelating agent. So actually you have diluted the sample by what factor? By what factor? You're going to figure this out tomorrow also. Half. Yeah. So whatever concentration you got from the calibration curve, that number you need to times 2 to get to the original concentration of the ion in the serum. Got it? Write this down somewhere in the recitation guide too. And then, of course, you need to measure the absorbance of the diluted serum at the wavelength, and then calculate the concentrations of Fe2 plus in the diluted serum, and then calculate the concentrations of Fe2 plus in the original serum, which is the number, the previous number times 2. Okay, the previous number times 2. And complete the only discussion questions and turn in everything to me, and then go talk to the group next to you and ask them, did patient A or B got abnormal ion level or not? Okay? That's it for the experiment. So the experiment is relatively simple. Okay? And let's pay attention on the recitation guide. So here, you need to write out these things in your pink copy, and note that this is like, you need to write out the absorbance at the wavelength, the certain wavelength for the diluted serum sample. And here for blank solutions, you need to add 500 microliter of hydroxylamine, 500 microliter, I think it's microliter of ferrozine, and 1000 microliter of deionized water got from the main hood. Okay? And for diluted sample, you're going to use 500 microliter of hydroxylamine, 500 microliter of ferrozine, and 1000 microliter of serum sample, either A or B. So take a look at the useful information. This week, instead of dealing with mole per liter, you will be dealing with microgram per deciliter. So you need to know how to do the conversion, at least for the pre-lab assignment. So let's use this as an example. So if you have 1.7907 times 10 to the minus 3 mole per liter of Fe2 plus, what you need to do, what you need to times or divide to get to microgram per deciliter of Fe2 plus. So we have talked about the conversion unit, right? And for sure you need to use it in some way. But there's still one thing missing here. There's still one thing missing here. Spend some time thinking about it, and then this conversion unit will get you from microgram, from gram to microgram, right? And this conversion unit will get you from liter to deciliter, some way. You're still missing one step, is to get you from how many moles of Fe2 plus to how many gram of Fe2 plus. Molar mass. And in this case, actually we don't call it molar mass because we call it atomic mass. But yeah, I think we're talking about the same set of number. Yeah, so look at a periodic table. Where is iron? It's transition element, so it should be in the middle part, and Fe, element number 26. See that? So, the number beneath it, let's just take 55845. What does this number mean, and where's the hidden unit? You call it molar mass. Why do you call it molar mass?
Moles per gram.
Moles per gram.
Yeah.
Moles per gram or grams per mole.
Grams per mole.
It's molar mass, right? So it's a kind of mass. But it's molar, so it means that the mass of something when you have a mole of it. The mass of something when you have a mole of it. So the mass of something in terms of gram when you have a mole of it. So here, you have this number. When you times the molar mass, you will see that you get to how many you get to, from mole per liter, you get to gram per liter. Already, right? And then you need to get from gram to liter to microgram to liter. So you need to get rid of the gram and get to microgram. So you need to invert the conversion unit that I have just provided. That's how you get from gram per liter to microgram per liter. And then now you need to get from microgram per liter to microgram per deciliter, right? And note that the liter is in denominator. So now you need to put the liter on top and then the deciliter at the bottom so that you can get rid of the liter. Anyone have difficulty following this? Good. So in the homework, you need to try to do this in not in the homework, in the pre-lab assignment. So yeah, you get a feeling it's not completely the same case, but if you know the trick, it should be. You should see them as the same case. So what's the number? It should be a very pretty number, and take 5 sig figs. One of the tips for TAs: stay hydrated.
That's true.
And actually, in the last lab, not the last lab, in the copper in the penny lab, you used a similar concept too. When you need to get from how many mole of copper 2 plus into how many gram of copper 2 plus in a penny, you need to times the molar mass. But back then, a lot of you weren't sure why, and this is the reason why. Because you need to know the ratio between how many, like the ratio of how many gram is in a copper when you have a mole of a copper. Okay? I give you 5 more seconds to punch the calculator.
I got 10,001.28.
So if I need to write that in citing notation, what would that be? Oops.
1 times 10 to the 4th.
10 to the 4th. How many sig figs I need to keep?
2.00. 1.00.
How do you know it's 2?
2 what?
How do you know how many sig figs you need to keep?
You said keep 2.
Oh, did I?
No, I
No.
said keep 5.
Keep 5. You start with 5 numbers. And
Okay.
you have 5 numbers here, you have 6, and these are exact numbers because those are conversion units. So 5, 5, 5. So 1, 2, 3, 4. Okay. And the unit is microgram per deciliter. Write it down so that as a double check. Make sure that you cancel every excess units except microgram and deciliter. Okay? Hint, this is the answer of one of your pre-lab questions. Okay? That's the reason why I come to Recitation. I'm not going to tell you which one, but this is the answer of one of your pre-lab questions. Okay, now let's move on to the second page. So here, some more lab questions. So here, a spectroscopic analysis was performed to determine the serum iron level of an adult male, patient 1135. Someone sit in that room perhaps. The calibration brought for absorbance at 560 nanometer versus concentrations of Fe2 plus in the standard solutions is shown below. So this is the calibration curve that person got. So here, the diluted serum sample of the patient had is at absorbance of 560 is 0.583. What's the iron level in the diluted sample? How do you get that number?
Use the formula and do that.
So you put the number into X or Y or R.
Why?
Why? How do you know that?
Because it's the absorbance, like the y-axis is absorbance.
Yes, correct. Because Y-axis represents absorbance value. That's why you plug the known absorbance into the trend line, like that. Into Y instead of into X. Today is 22.
3.
What?
Yeah.
Alexander's not here? Okay. Oh, Savannah's not here. So what's the number you got? What's the concentrations of iron in the diluted sample?
125.83.
120. You got 125?
Did you wrong?
Oh, I got a similar number, but I got what? 120. You round it up incorrectly. You need to keep only.
I'll try again.
You need to keep only 2 cyclic. So like.
Probably 120.
So I got something like this. Because you only have 2 cyclic here, so we only need to keep 2 cyclic. Okay. So how about what was the iron level in the original serum sample? How do you do that?
120 times 2.
Times 2. Yeah. So to be precise, is times. This is how you get to the number step by step. When you need to calculate the concentrations of an original solution before dilution, a lot of you will remember this equation, right? The original concentrations of the solution. The volume you have taken from the original concentration, the original concentrated solution for the dilution, the final concentrations, and the final total volume of the solution. So in this case, we know that C2 is 120 microgram per deciliter. The total volume of the solution, if you did the math correctly, should be 2000 microliter. And the V1 should be 1000 microliter. That's how you get the number 2. So actually that 2 has 4 cyclic. But because the number is pretty, you can just do the math directly. Got it? So 240 dilution factor. Okay, how about here? Question number 3. Based on the given information below, did patient 1135 have an abnormal serum level? It's an adult male, right? Adult male, the normal level should be around here, I would say 70 to 130 microgram per deciliter. But your adult male got 240, right? 240, it's here. It's an outlier. So your patient 1135 has an abnormally high serum iron level. It might be an iron poisoning, or he's been exposed to any kind of medicines that has iron in it. And if you are a nurse, or if you are a medical analyst in a lab, then you need to tell them that we need to do something to lower the iron level down before that person got iron toxic symptoms. Okay? So in the sample you use tomorrow, you might got someone that has abnormally low iron level, abnormally high iron level. You wouldn't know that until you compare that with the normal lab values. And in the lab manual, we have provided you the normal values in terms of a table instead of a bar graph. Okay? So, any questions about the lab? Nope. Let's go back to the lecture. Everybody enjoy kinetics, right? Here. So, let's review what we have learned so far about kinetic. So, we have learned about the rate law for 0, first and second order, and then we talk about the integrated rate law when you're doing the crystal violet lab. So, just as a reminder, you don't have to memorize this. These will be provided to you in the final page of the final exam, but it's good for you to practice how to write it because you need to know how to use it. So here, for an 0 order, the concentrations of the reactant at any given time is equals to the minus reactant constant times the times plus the initial concentrations of the reactant. And you don't have to know how to calculate the half-life because in biomedical science or domains, most of the time you're dealing with reactions with first order. So that's the only thing that matters for you. So for first order, the integrated rate law is the natural logarithm of the concentrations of the reactant at any given time is equals to the negative reactions constant, rate constant, times the times, plus natural logarithms of the initial concentration of the reactant. And for a second order, everything's the same except it's the reciprocal of the concentrations of the reactant at any given time is equals to the positive rate constant times the times plus the reciprocal of the initial concentrations of the reactant. You have no idea how long I practiced just to say that sentence smoothly. Okay, for first order reactions, how do you calculate the half-life? The half-life is equals to the reaction rate constant. I'm sorry. It's natural logarithm of 2 divided by the reaction rate constant. And this number actually is a constant number. You don't have to know about this one too. It's like 0.693 divided by k. It's the same number. It's so ugly, but you got the idea. So, here, let's look at the question. The first order reaction 2N2O5 will becoming 4NO2 and O2 has a reaction constant 6.0 times 10 to the negative 4 per second. Given the initial concentrations of N2O5 is 0.90 molar, calculate the following. The concentrations of the reactant at 30 seconds. So what you can do is very easy, just plug in everything into the calculator and then calculate it. So here, because it's first order, you need to use this equation. Okay? So natural logarithm of N2O5 at 30 seconds is equals to negative rate constant times 30 seconds plus the initial concentration, the natural logarithm of the initial concentration. So in the exam, this part is kind of more like I tell you the order, I tell you the initial concentration, I tell you the time, the reactant orders. You need to find out the concentrations of the reactant at any given time. It could be 30 seconds. If it's trickier, I will tell you that calculate when the time is 2 minutes. You need to convert 2 minutes into seconds before performing the calculation, but the mathematics should be the same. So what's the number on the right side of the equation?
Negative 0.12.
Yep. Does anyone have a trouble finding this number? If you're using a Texas, you should start from here, right? This number, and then write down, and then this number times this number, write it down, and then do the subtractions or additions separately. Okay? If you're using a graphing calculator, you can do that in one step. Or if you're using a casual calculator, you will be able to do that in one step too. So, negative 0.12. So how do you find this number? A lot of you will forget. Like, what do you mean by an anti-natural logarithm? Certainly, negative 0.12 is not the final answer, right? Because it's a negative number, and the concentration should not be a negative number.
Do something with the molarity.
Not yet.
Oh yeah.
The answer will be in molarity, but here. This is like the nature of logarithm. If you have, remember, if I tell you natural, the log of x is 0.1. So how do you find x? X is 10 to the, you correct 10 to the? 0.1, right?
So e to the.
It's because the base is 10. So natural logarithm is e. So May, you were raising your hand.
Yeah, I was just going to say it was going to be e to the negative.
So natural logarithm of negative 0.12 actually equals to logarithm of e, negative 0.12. So to find the answer should be e 0.12. Keep it in 2/16, you should get 0.88 more. Okay? Now I would like you to spend 1 minute to do questions B. I give you the unit in minute. You need to convert that into second before start calculating. It's exactly the same kind of questions but different time. Don't forget when you're doing this conversion from natural logarithm to the anti-log, you need to carry the positive or negative sign with you. So I got the number 0.84 molar. Do you get the same number? Okay, so you notice that after quite a long time, the reaction still hasn't dropped down, the concentrations of reactant still hasn't dropped down to half of it, right? So the next thing you need to do is find out at what time the concentrations of the reactant will drop down by half. Okay, you need to find out the half-life of the reaction. So what you're going to do that is you're just going to use the equation. Half-life equals to natural logarithm of 2 divided by the rate constant, 6.0 times 10 to the minus 4. You can do it in this way, or you can do it in this way. The natural logarithm of 0.40 equals to this. You will get the same answer. You can use this way or this way, you will get the same answer. If you use this way, you just plug in the equation and get a number. If you use this way, you know that the half of the reactant is 0.45 and you're finding the time. Okay? Instead of finding the final concentration. So you should get the same number.
Wait, where'd you get 0.45?
So this is this is the first way of solving the equation. Just plug into the given equation.
Yeah, no, I understand that. I was just,
This is
I
the second.
figured it out because it's not molar.
Can you repeat your question?
Never mind. No, I got it.
We're asking about the half-life. They should be in terms of time. So like, at what time the reactions where the initial concentrations of the reactant will drop down by half. And we know that 0.90 by half is 0.45. Right? So if you plug into the equations, you will get the same number. Okay? So what's the number? It's a big number. Just keep 2 sig would be sufficient. We can simplify it like this. Does anyone have an answer?
1.16 times 10 to the 3.
So keep it 2, it's 1.2, okay? Times 10 to the 3. What's the unit? Seconds. Because in the denominator is second to the power of -1, so when you flip it one more time, it will be +1. Okay? In second. So, I'm not going to talk about these 2 questions. Let's move on to this question. Questions 5 and 6, because they're all about how to use half-life, how to use the concept of half-life. So, I would like you to look at case 5. These are the only information you will be given, and I remember last semester we had questions like this in the open-ended questions. In the open-ended questions, just drawing. Super simple. You don't even have to calculate anything. At least not by using calculator. So here, at 0 day, you start with 8 gray ball. At 0.3, 4 of the gray ball disappear, becoming 4 of the 2 white ball like attaching together. Okay? So, what would happen in the 9th day? What would happen in the 9th day? So certainly when you see questions like this, it's about half-life. It's about half-life. So from the day number 0 and from day number 0 to day number 3, actually you can tell the half-life, right? So what is the half-life of this reaction?
3 days.
I'm sorry?
3 days.
3 days. So 3 days, the concentration will drop by half. Okay? Another 3 days, the concentrations will drop by another half, and then another half. So, by day 9, what would happen?
No gray balls.
There'd be one.
I'm sorry?
Just one gray ball.
So, okay, why no gray ball? Why just one gray ball? You start first.
Because they would just connect to each other. Because like if you go to 6 days, then
Mhm.
2 more would connect, and then 3 more days. 3 more would connect. Well, I guess that makes sense as to why there'd be 1, but how would there only be 1?
It always cuts in half, so 9 minus 3 is 6, divided by 3 is 2 half-lives, so you take half of that, so 2 would be gone, and then half of 2 is 1.
Yeah. So what she said is, at day 0, you have 8 gray ball. Day 3, you have 4 gray ball left. Day 6, you have 2 gray ball left because it's at the half of the previous one. And then day 9, you have only 1 gray ball because it's at half of the previous amount. So 1 gray ball and the remaining of them will all be coming the white balls. Got it? So just 1 gray ball. And here you can also tell that each direction is 1 gray ball becoming 2 white ball. Right? So 1 gray ball and then 7 pair of white ball pair. Just draw it in whatever way you want. Okay, that would be the correct answer. I'm going to leave you to do question number 6, but let's look at a reaction. This is slightly difficult. Slightly difficult. Again, you start with 8 gray ball. And then in 4.5 seconds, you got 4 gray ball left, but you have 1, 2, 3, 4, 5, 6, 7, 8, 8 diamonds. 8 diamonds. So what's the reaction? A gray ball become 2 diamonds, and they are not attaching each other. Okay? So in 9 seconds, it's how many half-life? It's the second half-life, right? Second half-life. So how many gray balls you should have? 2 gray balls. And then the tricky part is how many diamonds you should have.
12.
12. Because 2 more of the gray ball will become 4 diamonds. Is it 12? Let me do the math. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, 12. Okay? Again, I will show you the detailed answer today. I'm going to send that to you by email, and if you have any questions about the recitation guide or the lab or the homework, approach me in the office hour, which is in 10 minutes in my office. Otherwise, you're dismissed, and I'll see you tomorrow at 8. Don't forget to turn in your pre-lab assignment. I do have more than 2 people forget to turn in the pre-lab assignment last time. Okay? See you later.